Here we go. Good. All right. Okay. So if we take, for instance, x to be 1, right, what happens? Well, if you replace x with 1, we're going to get 2 times 1 plus 1, right? And that's going to equal to, but that's equal to 3. So the equation here is going to be 3 equals 2. This is basically the left-hand side. 2 times 1 plus 1 is 3. So 3 equals 2, but that's false. Right? Remember, equations can be true or false. When x is 0, right, we have 2 times 0 plus 1, which equals 1. So in this case, we have 1 equal to 2. Well, that's false also. So this is false, this is false. But what if we replace x by a half? Well, in that case, we're going to get 2 times a half plus 1. That's equal to 1 plus 1, which is 2. So this equation then says 2 equals 2. So when x is a half, we get a true statement. I mean, we have x here alone. We don't know if that's true or false because we have a variable here. Okay, that's good. So we get a true statement when x is a half. So there is a value for the variable that makes the equation a true statement. Such a number we call a solution of that equation. So any value of the variable that makes the equation true, we call that a solution. Some books call it a root. I call it a solution, though, of the equation. So a solution for an equation in a variable, it's a value for the variable that makes the equation true when you plug it into the variable. That's all we're saying. Now, if you want to actually find the solutions, which you guess we're going to do, the process of finding all the solutions is what we call solving the equation. That's what we call solving the equation. Okay. And then we have this notion of a solution set. And again, we said a set is just a collection of stuff. For us, usually it's going to be a collection of numbers. Well, the solution set, that's just a collection of all the solutions for that equation. It is possible it could be empty. That can happen. There is such a thing as the empty set. Yeah. And this will come up actually shortly, but there is this notion of two equations being equivalent to each other. By definition, that just means the solution sets are the same. So they have the same collection, they have the same solutions, in other words. So two equations are equivalent to each other. They're equivalent equations if they have the same solutions. All right, now I know that's a lot of vocabulary. We did just mention, solving equations and stuff, finding the solutions. I mean, here basically we guessed, right? We just plugged in numbers. But guessing is really not the best way to solve an equation, though. A good way to solve it is actually manipulating it. But you can't do any manipulation you want. You have to do certain manipulations. Namely, you're going to manipulate, you're going to mess around algebraically with an equation to try and get one that's easier to deal with. Right? So again, let me go back. I think, I should have stayed on this slide, but that's okay. For this equation here, right, if we were to actually solve it, we can actually manipulate this, play around with it using algebra and rewrite it as an equation that's much easier to deal with. But again, you can't do anything you want. There's only certain manipulations you can do, and that's what this is telling us. So what you can do is this. So these are the manipulations you're allowed to do, you're allowed to use to solve an equation. This is what you're allowed to do when you solve an equation. You can simplify either side of an equation. No, you could simplify it. You could add or subtract the same expression to both sides. You could do that. I know they have here the same domain, okay? With the same domain, in other words, as the original equation. I mean, for us, really, it's not going to be too much of too big an issue. But you basically can add or subtract the same thing to both sides of the equation. You could multiply or divide both sides by the same non-zero real number, and you could interchange both sides of the equation. So let me say it again. When you're solving an equation, okay, there's only certain manipulations you're allowed to use, right? You want to rewrite an equation such as this into a much easier form where it's obvious what the solutions are, or at least it's a lot easier to get the solutions. But these are the manipulations you're allowed to use, or you're allowed to use. And now why is that? Because it turns out these are not going to change the solution set. You know, the solution set of the first equation, the one you start with, and the last equation you end up with that you're trying to solve, they're going to have the same solution set. You're not changing it. In other words, if you have an equation and you use any of these manipulations on it, the equation you get will be equivalent to the one you started with. They'll be equivalent. Okay, and that's good. That's what you want, right? You don't want to lose solutions in the process. And you don't want to add solutions in the process, because the whole point is you're trying to solve the equation you started with. All right. Now, for now, I mean, what I just said applies for any equation. For now, let's just focus on linear equations. That's an equation in one variable. That's an equation that looks like this. Or it can be written meaning it's equivalent to this. It's an equation you can write like this. And this is, again, where A, B, and C are numbers such that A is not 0. Here I wrote can be written. More formally, it's equivalent to this. Where, again, A, B, and C are numbers, but A is not 0. I mean, technically, this is also a linear equation because these two are equivalent to each other. You can actually take this equation and manipulate it to get an equation in this form. And what's nice about this one is the only solution to it is the number D, whatever that is. And that's generally how you're going to solve these linear equations. You're going to take this equation, the one you started with, and manipulate it. Using these manipulations, you're going to end up with something like this. And this is actually easy to solve. So, okay. Are there any questions so far? I know that was a lot. I understand that. All right, well, let's actually do some examples. So let's suppose we have this example, which we saw before. I mean, yeah, we solved it by guessing, but let's solve it by using those manipulations. The whole point is you want to get x all alone. That's really what we want to do. No, you want to get x on one side and everything else on the other side. Okay, so we have 2x plus 1 equals 2. Well, if we want to get x all alone, let's subtract 1 from each side. Okay, what's that going to do? Then we get 2 times x will equal 1. That is 2 times x equals 1. This one is actually equivalent to the equation we started with. So they both have the same solution sets. Okay, now this one's pretty simple, but let's make it even easier by getting x all alone, right? We want to solve it, meaning we want to know what x has to equal. So let's divide both sides by 2. And we end up with 2x over 2, right, equals a half. Of course, this is the same as x. So we get x equals a half. That's what we end up with. Okay, so this equation, the only solution to it is when x is a half, right? You know, if you replace x by any other number, the last equation is going to be false. So the only solution to this is a half. This is the solution set. And so the solution to the original equation is a half. All right, that's good. Okay. All right. Let's do some others.